All right, here we go. Homework 4, part B. So this is the first part that we are going to be looking at. We need to write and explain Python code using this polynomial situation with this transfer function situation where we want to multiply transfer functions in series. So if we hop over to Collaboratory, I'm going to quickly just paste in my libraries that I'll be using. These two will be the focus for right now. Something important to note, so if we use P and then just throw a few numbers in, you can see that this is going in ascending order of power. So this is x of 0, x of 1, x2, x of the third power. It's an increasing order. For transfer functions, a little different. You need a numerator and a denominator input. So what this looks like, it's in descending order. So this one would be s squared plus, or s cubed plus 2s squared plus 5s plus 6 divided by s squared plus 2s plus 3. So that's something important to note when we are going to be dealing or bouncing in between the polynomials and transfer functions within Collaboratory. So first we want to define a function, transfer function to polynomial. We need a transfer function, obviously. So from that transfer function, we are going to return the polynomial. We are so when you get a transfer function, it's going to be in the form of numerator, denominator. So we are going to grab the numerator from there, and then we need to reverse the order of that. So what that looks like is start, stop, and then the step. If we set that to -1, that reverses the order. So it gets the correct power is what we are looking for. And then obviously the denominator. Same thing here with the indexing. Need that backwards. So yeah. And then we want to do a polynomial to transfer function. And then from here, we need a numerator and denominator. And then we are returning, we want that transfer function. So from here, we want num dot coefficient to grab the coefficients index backwards again. And then the denominator, same thing, index backwards. And then if we want to multiply transfer functions, we'll call that TF mult. We need two transfer functions. So TF1, transfer function 1, TF2, transfer function 2. So what we're going to do here is we're going to get the numerator and denominator of the first transfer function. And to do that, we are going to do poly or TF2 poly. And if you look here, it's returning this transfer function numerator denominator. So it's splitting those there. So basically we just have to do TF2 poly for our transfer function 1. And then similarly for the numerator and denominator, we use that function again, however, with our second transfer function. And then we want to return, since we're converting this into the polynomial situation, we're going to have to do poly to transfer function. And then our numerator is going to be n1 times n2. And then our denominator is going to be d1 times d2. So that is what we need for how we can multiply transfer functions in series. And then we can now jump into what we want to derive as a transfer function for a PID controller. So I'm going to hop onto my iPad really quick. Okay, so now we want to get the transfer function for a PID controller. So we're going to kind of investigate that really quick on my iPad here. So there's three components: the proportional component, the integral component, and then the derivative component, so PID. That's represented by the proportional components represented by this Kc value, where we're multiplying out. This is the proportional gain. So there's this E value. This is a deviation variable where that is, let's say, some set point subtracted from our output variable. In this case, h just means height. So we're adding 1 over tau I, which is the time interval, and we're integrating starting from 0 to t of this error with respect to time. So this is the integral portion of the controller, and then we're adding tau d multiplied by dE dt, and this is the rate of change of our error. So if we take the Laplace transform, what this looks like, we're left with Kc and then E plus 1 over tau I. The Laplace transform for an integral is just E, we're left with that E again, divided by S, because the Laplace transform of an integral is 1 over S, and then plus tau d times, so the Laplace transform for this would be E times just S. And then if we pull out E, we're left with 1 plus 1 over tau I times S plus tau d times S. And then if we want to get a common denominator, we keep moving forward. We multiply by tau I times S times, or divided by tau I times S. So what that looks like is this. All divided by tau I times S. So now we need to keep in mind that for the transfer function, we are looking at numerator and denominator, and that also it's in descending order. So let's rearrange this again so that we have a descending order for the numerator in this case, because the denominator only has one term. So the first term is tau d times tau I times S squared plus tau I times S plus 1. So that's our numerator. And then we divide by tau I times S. And then as you can see, the numerator is also being multiplied by this out front as well. So to kind of see what like a feedback loop looks like, so let's say we have some process here. It's a single tank. So kind of the transfer function to reflect that is that there's some resistance R1 for tank 1 divided by the denominator is A1 times R1 times S plus 1. And this was derived earlier for a tank. And then what we're inputting in here to this transfer function is some flow rate QC. And then out from there is some height H1 for tank 1. And then this is getting inputted into another transfer function, 1 over R1 in this case. And then this is outputting Q2. So that's the flow rate for tank 2. And then similarly for this transfer function over here, we have R2 over R2 times A2 times S plus 1. A is the area. And then this finally is outputting H2. And let's say that's what our output that we're looking for. So where does the controller come into play? So we have our controller on this side here, where this transfer function would be. So this is our controller. And then all of this would be kind of considered the process. Here, this is where the backwards loop begins. So we have this input into some measurement device. In this case, it's kind of a unit conversion. We're just going to multiply by 1. And then this gets inputted all the way back up here into comparator, where the input, what we're adding, is going to be our H2 set point. And then this is going to give us our E, our error. So kind of like what I was explaining up here earlier with this here. So if you look, the forward transfer function for this feedback loop is all of this being multiplied, and then the backwards feedback loop is this component right here. So if we want to look from, let's say, QC to Q2, we multiply this transfer function by this one. And then as you can see, there's some cancellation here of R1, the resistance 1. And then we'll kind of explore that more in Python. So this is the transfer function for the PID controller itself. And then we'll get into what adding or multiplying all of this together to get one sort of transfer function for a feedback loop looks like in Python. So let's jump back into our code. Okay, so now we're back in Python. What we want to do is make a new function. We're going to call this PID. There's 3 components we need to consider: our KC, our proportional gain, our tau I, time interval, and then tau D with respect to the derivative. So what we want to do here is return the transfer function. So again, numerator, denominator situation. So our numerator, I'm going to be looking at my iPad for reference, what I just wrote. Our numerator in descending order, we start with KC multiplied by tau I multiplied by tau D. So this is our S squared term. Our S to the power of 1 term is just tau I times S. So we omit that. And then we had a plus 1. But we multiply also by KC, which is important. And then on the denominator, we just had tau I, but this was multiplied by S. So we have to say that our constant term is just 0, just to make sure that we have that. So let's take a look. Let's say our KC value is 1, our tau I value is 0.8, and then we'll have a tau D of 0. So this gives our transfer function. So this is S plus 1.25 divided by S. So that is the transfer function for our PID controller. So now we can look, we need to look at what the block diagram looks like in terms of GC, GP, GM. These are all transfer functions. So the transfer function of the PID controller, transfer function for the process, and then the transfer function for that measurement device. And then we're going to get that transfer function relating all of these together. So we're going to jump back into my iPad so I can explain a little further in that regard. Okay, so we're back on my iPad here. Kind of simplifying what we had up here, this feedback loop situation. So we want in terms of So this is our process GP. This is getting inputted. The input here is coming from our controller GC. And then finally, this is giving us the output H2. Again, this backwards loop here feeds into a measurement device, GM. Where this is sending the result to the comparator, where we are looking at the set point and then subtracting this H2 that we measured in the process. So if we want to get an equation for H2, this is going to be the difference between the set point and what we measured multiplied by GM, that measurement device. And then if we go across, we are multiplying by the transfer function of the controller and the transfer function of that process to finally get H2. So we're just multiplying by GC and GP. If we split this out a little bit, we are left with an expression that looks like this. And then if we move this term to the other side to collect our H2, get 1 plus GM, GC, GP. This equals that H2 set point multiplied by GC, GP. And then if we divide to isolate H2, we have this H2 set point multiplied by our numerator is GC, GP. And then our denominator is 1 plus GM, GC, GP. Now, if we consider kind of what the forward direction and the backwards direction of our loop is, our forward direction is this top part here with GC and GP, and then the backwards portion is this backwards loop back to the comparator GM. So GM is the transfer function for the measurement device, and that is the only sort of the component for the backwards part. So if we define GC, GP as the forward transfer function, we know that transfer functions have a numerator and a denominator. So we can call this NF for numerator forward, and then denominator forward is DF. And then if GM is the backwards one, we can say NB over DB. So if we substitute here, we're going to just omit H2 set point. So GCGP turns into NF over, DF, divide all of that, get 1 plus our numerator backwards divided by our denominator backwards multiplied by numerator forwards divided by the denominator forwards. So if we get our denominator to have a common denominator, what that looks like, we have NF over DF again. Sorry for this line situation. DF, so we're multiplying by dBdF over dBdF. So we have dBdF plus NBNF all divided by dBdF. And then if we want to get this in single fractional form, this is just NF over DF multiplied by the reciprocal. So dBdF divided by dBdF plus NBNF. You can see these terms cancel, and then we're left with NF times dB divided by dB, dF plus NB, NF. And this is sort of how the transfer function is going to look in Python once we get back into there, which we will do right now. We're back in Python here. So kind of refreshing on what we're doing. We explained this situation, and now we're going to get the servo transfer function in terms of the numerator and denominator polynomials of the forward and backward transfer function. So to do that in Python, we need to define a new function. So we're going to say tf feedback, where we have a forwards transfer function and then a backwards transfer function. I'm going to define that like this. So the numerator forward and then the denominator forward, kind of the nomenclature we were using on our iPad here, that is going to come from, so we're getting a transfer function. So we want to go to a polynomial for the ease of performing all of these things. So we're going to do the TF to poly for that forward transfer function. And then similarly, our numerator backwards and denominator backwards, we're going to retrieve from our polynomial of the transfer function backwards. And then from there, we want to return. So since we are working with now into polynomial, we need to go back to transfer function. So our numerator was, I'm going to be looking at my iPad again for reference right here. This expression we got, so the numerator is the forward numerator multiplied by the backwards denominator. And then our denominator is the backwards denominator multiplied by the forward denominator. And then we're adding the backwards numerator multiplied by the forward numerator. So that is kind of how we can express what a feedback loop will look like in terms of a forward and backwards transfer function. So now we can go into this part B2A, looking more specifically at given parameters for our PID controller, and then our areas and then resistance are given. So let's get into that part now. So we kind of got transfer functions for from QC to Q2 in that block diagram, and then from Q2 to H2. So we want to essentially get transfer functions in the forward direction, which we get from multiplying the controller by the process. The process is sort of these two transfer functions here we're going to be multiplying. And then our backwards transfer function is GM. We're setting that to 1. So what this looks like in Python, we're given that A1, A2 equals 1, R1, R2 equals 2. So let's initialize that. Two equals 2. We are also given the proportional gain is 1, tau I is 0.8, and then tau D is 0. So we can input those there. So now what we want to do is multiply across everything to get the forward transfer function. So we can get the transfer function from QC to Q2. This is going to be a transfer function. The numerator. So if we scroll back up to what I had here, I guess I can show here as well. Or not. We're multiplying that R1 over A1 R1 S plus 1 by 1 over R1, which is this equation multiplied by 1 over R1. So our numerator is gonna, so that R1 on top from the input of the flow rate, that numerator is R1, so that cancels. So our numerator here is just 1, and then our denominator turns into A1 times R1 times S. So, and then we have plus 1, so there's that one. And then from Q2 to H2, that's another transfer function. That one is just our R2 in the numerator, and then our denominator is R2 times A2, and then our plus 1, so there's that one. And then if we multiply these, so our first transfer function is QC to Q2, and then our second is Q2 to H2. This we can call QC to H2. So now we want our entire forward transfer function. So that's going to be our controller, our PID controller multiplied by this here. So we do TF mult again. Our first transfer function we're going to call our PID function that we have up here because it's returning this transfer function. Our KC is given, our tau I is given, and our tau D is given. So that's our first transfer function, and then our second is QC to H2. So that is our forward direction transfer function. So now if we want our transfer function under feedback control, we're gonna kind of rename that this. This is the transfer function of this one forward. And then our transfer function backwards is just 1 over 1. Oh yeah, right, sorry. Into let's just make this one a transfer function. So parentheses, maybe not. So the numerator is, so this is the forward, and then the denominator is the, let me continue from my confusion. So we need to go back to this function that we called. So that is our TF feedback. And then this is receiving a forward transfer function and then a backwards transfer function. So our forward one we just created right here. So that's called TF forward. And then our transfer function backwards is just 1 over 1 because that is our measurement device GM, and that is set to 1. So if we just do shift enter, this is our final transfer function with feedback control. So yeah, we'll dig into the step response and then this final part next. So we want to get a step response from the transfer function we just created. So that's going to look like this. However, we want to input some sort of time system here. So we're going to make a time plot, call it t-plot. Go from 0 to 100, and then we'll do 500 points in between. And then we're going to set that our time interval to that time plot. And then as you can see, we are given two arrays. One is the time one and one is the response. So we can rename our time plot and then give a name to that output as just H2. So now we can go ahead and plot this using Plotly, where our X will be our time plot, our Y will be that response H2, and then we can update layout of our plot where our width, let's say 600, height of 400 pixels, and then update our layout or our template to be Plotly dark for the class favorite, easy on the eyes. So basically what you can see here, this is, you can see these oscillations are diminishing as in response to that step response, and it's finally going to eventually converge. If it were the other way around where it began here and began to increase in oscillations, that means our system would be unstable. So now what we want to do is simulate just the response of the forward transfer function, the response to that to a cosine error input where the amplitude is 1 and then the frequency is 1. And then we're going to superimpose the input and output here. So what we want to do, we want to make a new time plot. We'll call this tsim from 0 to 50 this time, still with a lot of points in between. Our frequency is given as just 1. That's in radians per second. And then our error function is this sort of cosine function. That is, so earlier we had a step response, now we're having like this sinusoidal response. So that is just our frequency multiplied by this new time. So we have that. And then if we want to go ahead, we want to do LSIM under the signal. We want a system where we can do either a state space system, transfer function, any time invariant system. And then it needs an input. Our input's going to be E, and then our time. So what we want to do, this also kind of looking really quick. So sorry, our returns, it's going to return 3 different things. One is the time values. The thing we're curious about is this Y out. This is going to be our new H2, and then this is kind of a response for state space, which we're not really interested in. So since it said that we want to look only at the forward transfer function, so GC and GP only, so no GM, our sort of system will be that forward transfer function. Our input is going to be E, and then our time will be our new tsim, and then our first variable we're not concerned about, so we can use an underscore. H2 is that Y out, and then that X out we're not concerned with either, so we can save that as that, and then we can make a second plot. So do this, and then we're going to add our input and output, and we're going to superimpose that. So add scatter where our X is tsim, Y is H2, and then we're going to name this output since H2 is a response. And then we're going to add another scatter plot. X is still that same time plot, and then our Y is now our E. So this is our input. So we're going to name accordingly. And then we can update the layout again. Width 600, 400. Template. Forgot an equals sign. Let's see how this looks. So as you can see, our input begins up top, and then as a response, this is our output. But an important thing to note is that the amplitude of our input is greater than the amplitude of our output, meaning that whatever is going into the feedback loop is coming out in a smaller degree. It's not being amplified, and therefore this is also an indication that our system is stable. And then if it were the opposite way around, then our output amplitude would be greater than the input. And that should be everything that we need to cover for homework for part B. So thank you.